Okay. Okay, great. Thank you everyone for joining the IceCube Neutrinos in Deep Ice competition third place winner call. So I'll pass it to Deepam for the presentation of the solution. Oh, I think maybe he clicked on wrong button. Okay. We'll wait back. We'll wait for him to join back.
Yeah, so sorry about the technical glitch there. Basically, it asked me to reopen the browser to share the screen. Yeah, okay, I can get started. All right, is it visible now?
Not yet.
Okay.
Oh, we can see it now. Thank you.
Yeah, so hi, yeah, my solution for the IceCube challenge was essentially I went with a transformer. So I actually did some work with other models, especially the graph model that was shared early that had a lot of good insights. But after reading the papers, what I decided was I will go with the transformer because essentially what it felt like Dyneage or any other models, they were sort of there's no reason why this data seemed like a natural graph. Like we were kind of artificially picking the edges, and it only seemed like more natural to use a fully connected map, which transformer is sort of like a fully connected graph of all the data in the sequence. So I went with that. And with that, the first solution that I tried, which went a long way, was using classifiers. Training transformers proved somewhat difficult, unstable with many different kinds of architectures. But as classifiers, basically just binning the angles separately, that seemed to be more stable. And I wanted to quickly try ideas, so I went with classifiers. And interestingly, if I use the von Mises laws, which basically is predicting a 3D vector and using that to get the angles, that was way more unstable with the transformer. But if I just use the a trained transformer, pre-trained transformer on the classifier, and then fine-tune that model with the 3D vector predictor, that actually performs even better than the classifier. So that was interesting, and I think combining these was my final innovation that really pushed me on top of the leaderboard. And yeah, so that's kind of one picture for the solution. And moving on, so my background, essentially, I'm a master's in electrical engineering, and I don't have too much experience training transformers as such. I work as a machine learning engineer, mostly for deployment of models and some experimentation. But for training transformers, I've not done that much. I've just read about them. But this was the first time, and thanks for the opportunity. That's why it was a really good learning experience training transformers, and it worked out well. Okay, so in a bit more details about the solution, what I do, as we know that the data is a sequence of pulses, like temporarily, we know temporarily when each pulse occurred and at which sensor location. So all those are basically one sequence as just passed to a transformer, and I take the length up to 256, and some there were of course, as I said, the classifiers and then the 3D vector regressors. They slowly started combining them, actually starts improving the scores. So just with the classifier, I was able to get to 0.982, which was like maybe 10th or 11th on the leaderboard. But with these further improvements, where there are these very long sequences, which it's very hard to train a transformer. It's actually squared in memory to train. So I was able to fine tune with this higher batch size, higher sequence length, and then finally combining it gave the final score of 0.965. And actually use an ensemble. I didn't have too much compute available as such, and only trained it on my own home machine. So I just use two of these transformer models and I take two checkpoints from one of them, and that actually got me the fourth to third position. But I mean, the scores are very similar still. So this is the hardware. I actually had a 3060 before, and only in the last month, 20 days of the competition, I decided, okay, doing better in this competition does require some more compute. So I upgraded it to the 4080, and everything else is quite normal PyTorch and flash attention that actually really help train much faster. And yeah, so things that were important, using both the pulses was important. I did do a lot of analysis, EDA on the data of okay, why might the auxiliary pulses be important. It does seem like sometimes the auxiliary pulses also carry some information of getting activated based on the correct direction. So that's sort of what my hypothesis is. Not tested it well, but I think using them both was quite important for the score. And yeah, I subsample the sequences with priority to these real pulses still. But I mean, the score for the longer sequences is very, very long, very less already. And yeah, so one thing that made sense is, I think Philip had also mentioned that we don't want to use the absolute time, we want to use the relative time for the pulses. And so I subtracted the first pulse's time from the entire sequence to set it to 0. And yeah, and I also included scattering and absorption data that was actually shared by the early sharing prize winner Datasaurus. So even that was quite helpful, and it does improve the score a little bit. And the final training time is about 4.5 days, and the further fine tuning time is quite less. The main model actually takes most of the time. Okay, so by the way, is it should I keep on talking about or just the details, or are there more interesting questions that maybe the organizers have?
Yeah, I think it depends what you prepared. I mean, if you have more slides on the details, then we're happy to hear them, and then I think there's still time for questions.
Okay. Yeah. So basically, what I used was these 18 layers of 512 embedding size. This is actually a more taller, I mean, more layers, but less than what a normal GPT-2. If you look at the GPT-2 scaling numbers, they use a bigger embedding size versus like less layers. But what I did find from training much smaller models was the number of layers seems to be more important for this data in particular. And that's why the final thing has more layers overall. And this loss that I think it does help, that what I wanted was uh, the classifier. Of course, if I just train with one hot encodings, which is the normal way to train classifiers, all the labels are independent. Versus here, we know that okay, if the angles are close, they are actually more preferred than simply having all the angles to be independent. So basically, it's quite simple. If it's one hot encoded to this angle, just do a simple Gaussian smoothing, and it will bring the value down somewhere close to 0.13, and the rest of it is also all the other a lot of the other bins also get the some value. So it's not exactly like normal label smoothing. This is sort of something that is more applicable here. And as you know that azimuth has wraparound, so even this has wraparound, and the zenith I chose to extend beyond 0, which does not physically make sense, but it worked for actually training. So you use that, and then during inference, I just clip the, if it predicts something that is beyond 0, I just clip it. And yeah, so this is sort of how the scaling worked. I had tried a lot of other ideas about augmentation and everything else, but this is the thing that actually for transformers seems to help. And even though I knew that, okay, I've not trained these very long, very big models before, that it'll take maybe 4 or 5 days to train, and I don't know what the result would be. I decided, okay, it does seem like a little bit more, I mean, going bigger does seem to have the score, so I have to go for it, and that paid off. So what I do see is that throughout the competition, I was not seeing any overfitting with the transformer and classifier setup. Only at the end, when I trained maybe about 3.5 epochs on the entire data set, that's where I see some overfitting at the end. And okay, so and this sequence length as well. So what I was trying initially, I think the early sharing solution as well had used only lengths up to 64 or something close to that, and that seemed like, okay, if we check the data set, there's only about 52% of the data which is up to that length. So when we subsample, we're actually cutting out a major portion of the sequences. So what I tried first was, okay, if I just train it over 64 and then I fine tune, that actually does improve the score like very fast, but it does not reach what a fully end-to-end trained model would do. So and by the way, all these details that I'm presenting, they're for smaller models, and then I only train the big model at the end. So that this one was quite helpful, using up to 256. I think above that probably does not help too much. I do fine tune on 3072 only a little bit. Okay. And then for speed up of the training, I mean, of course, I'm doing on less compute. So these were kind of very big wins for me. As such, by packing the batches, I think got about 3x speed up, and just using flash attention and things like that. Overall, I think naively training versus all the engineering setups, tweaks that I did probably gave me about an 8x speed up. So that was quite helpful. Okay, so then we have just details about the hyperparameters. These are pretty standard nowadays. I mean, things keep changing really fast, of course, but they're standard to use the GELU activations or different style units. GPT is pretty common, so that's what I went with, RMW optimizer and 64 head size. And what was pretty sensitive was the learning rate schedule. I did tweak it a lot on the smaller models, and finally went with this one cycle, which is like cosine with like warm up, and then finally annealing down to a very small value. And gradient clipping as well does seem to affect towards the end of training the stability of the thing. Coming to the other one, which combining these both finally was quite helpful, but it was unstable if I trained it directly. So if I see the predictions, I go ahead and show plot. If you see this classifier, it's actually very heavily biased towards the upper side of the IceCube, which at least my hypothesis is that is because of the muons that are coming from above. There is this one spike which I did not find a good answer for why it's predicting for that particular angle. But it was crucial that, okay, I did some other model if it's able to get a better, more correct estimate of the zenith. So this model, the 3D regressor, was pretty good at doing that. And at first, what I observed was the GraphNet baseline. It actually had a lower bias for that particular site. So that's was my motivation, that okay, if I can fine tune on top of the transformer, then it might be helpful, and it was. And training this was pretty simple. It's a simple MLP, and I just actually train it for way more epochs overall. But it reaches pretty much a bit better than what the original classifier was able to reach. So yeah, that's just that. And I use the same hardware, and just takes only about 4 hours to train, and 2 hours to actually cache all the. So I just dump a lot of batches, the outputs of the encoder, and then I use that to train instead of training the whole thing end to end. Okay, so this up to this, I think combining these two gets maybe around. It actually does get up to 4th in the leaderboard, but this last one, where I only got this idea maybe 3 days before the end, which helped a lot. Is that okay? These predictions are quite different, and as you can see that, like, both of them have their own biases. Like the stack predictor actually wants to predict these edges a lot, versus the classifier, as I said, is biased wholly towards the top of the IceCube. So and on top of that, they're quite it's not very close to the perfect prediction that you might get. Like, normally when we train neural networks, we already might be getting a very high score, and then that's when doing ensemble with both of them maybe gives a little more. Versus here, there's a lot of room for improvement. So I thought, okay, we can maybe try this other ways to ensemble. And I was writing some simple rules about, okay, if it's here, if it's too biased, maybe, if the predictions of the classifier are sort of towards the top side, or maybe around here, then maybe I want to give some lower priority to those values. I was writing some of those rules, and they seem to improve the scores. So I decided, okay, this seems like a normal decision tree. I can use something like a boosting method, and that actually worked really well. So for boosting, I use simple use scikit-learn's histogram gradient boosting classifier, and just I'm combining two models, so it's just a predicting which one to take. And with that, I was able to get a significant boost in score. Also, these two different models, which I trained, one is 15 layer, one is 18 layer, they also had some level of disagreement. So I thought we can try out ensemble. I did not do a lot of experiments. It's basically last day of the competition almost. And just using an ensemble did help. And later, when I was checking, okay, what were the features that were helpful, does seem like that it looks at the kappa and the predicted probability of the base model, which we can use the softmax for the probability values as a proxy for the probability values. And sort of it's looking a lot at those values itself. But one thing was interesting, which is this time minimum, which in this case, the case of the combiner, when I was writing rules by hand, I was not using the time at all. But when I use the boosting model, I use the time values as well. And there I did not subtract the relative time. So later I found out from the second place solution. He pointed it out. I was not aware of it, that technically it's a leak from the simulator, that some directions might take more time, and that's why it seems like using this does give some effect on the scores. And I tried removing it. It does not affect it dramatically, but it does affect it to maybe bring it down at least from third to fourth. So maybe I got lucky with this. I'm not sure whether other people are using the leak as well, but yeah. So some ideas that failed, I did spend a lot of time trying to find out how can I make training faster. So if there is some noise in the data set, can I filter it out? And maybe that will, of course, if I can filter out 50% of the data set and still get a good score, then that helps me train bigger models. But was not able to find any significant portion of the data set where this can be removed and does that. Then, of course, the 3D vector regressor, as I said, was quite unstable. I tried a lot of hyperparameters, but was not able to make it work. And also, in general, in machine learning models, when we see some prediction bias, maybe we try to do it by giving more weightage to the other predictions, maybe overtraining, oversampling them. But in this case, it still did not help the classifier to balance the predictions better. So all of these were failed ideas. And for improvement, what I had seen was essentially there was no overfitting, but later when I saw some overfitting at the end, we do want to use maybe some other methods to reduce the overfitting. So these are some methods which might help to regularize, like supervised contrastive learning. Basically predicting the angles between two sequences instead of just predicting what was the angle for one sequence. We can predict the angle between two events. I tried that, and it was good for small models, but as I scaled up, it was not helpful. But maybe if it's overfitting, then this might help. And the angle classifier, I'm doing two separate sections. If I do it on a single prediction for one spherical section, that might also improve the results. So that's all. That's all from my side. We can go for questions.
Thank you. Thank you so much for the presentation. So we'll open the forum for any Q&A. Yeah. Please go ahead, Philip.
Okay, yeah, thanks a lot for the presentation. I can start with just a few questions to kick off the Q&A. So my first question is quite a general one, and I think it was partly answered on your last slide. So my question is, had you much more compute available, what would be the things that you would change to further improve the model?
So of course, one thing I would do is train a much bigger one. That did seem to pay off a lot, except for the overfitting towards the end. And the one where I'm pretty sure that what the supervised contrastive training that I had prepared, I only dropped it maybe after one day, where I saw, okay, I tried on a small model and then I scale it up, and basically it gives the same result. Because it was not overfitting, I think I decided to drop that idea. But if I see more overfitting, which is likely